One standard algorithm for traversing graphs is known as breadth first search, or BFS. Basically, if we have some highly connected graph of some sort, or it doesn't even have to be highly connected, but just say we have some graph and we have some starting point, breadth first search will visit the nodes in this graph starting at the starting point and then going in layers away from the starting node. So from closest to the starting node to furthest from the starting node in terms of an unweighted distance. So in terms of number of edges away from the starting node. Because of this, BFS is commonly used to find the shortest path from a given starting node to any other node in the graph. The algorithm is as follows. Basically, we have some q to represent distance node tuples, and we start by adding 0 start to that q. So start is the starting node, and the starting node by definition has 0 distance from itself. So we add 0 start to the q. Then while the q is not empty, we pop the next element from the q. So we pop the next distance node tuple, where cur is the node, d is its distance away from start. And if cur has not yet been visited, we mark cur as visited and we say that it has d distance away from the starting point. And for each outgoing edge going out of cur, so for each edge cur w, so cur going to w, if the neighbor w has not yet been visited, add d plus 1 w to the q. So for each of cur's neighbors that haven't been visited, add that neighbor to the q, and the distance associated with that is 1 plus whatever distance cur has, because that node must be one node further away from the starting point than cur. So here's an example graph. It's a directed graph, and let's see how this works. So I'm going to draw my q over here, where the top is going to be the front of the q, and I'll add things to the bottom of the bottom will be the back of the q. So I start by adding 0, and I'm going to start my BFS at A. In general, with BFS, you specify a starting node. So I'm going to start at node A. So node A is my starting node, and it's 0 distance from itself. That was step 1. Done. While the q is not empty, it's not empty, I have one element, pop the next element from the q. So I pop 0 cur from the q. Okay. I'm just going to always have the top thing being whatever it's popped, just so I don't have to keep redrawing stuff. So if cur has not been visited, nope, I've never visited A, I mark it as visited, and it has a distance d. Then for all outgoing edges, so A has one outgoing edge, A to B, if the outgoing neighbor, so if W, so if B has not been visited, nope, it has not been visited, add D plus 1, so 0 plus 1, W, so the neighbor with distance D plus 1 to the Q. Okay. So while the Q is not empty, it's not empty, I pop D cur from the Q. Okay, so I pop off 1B from the Q. So B is my current node, 1 is its distance. If cur has not been visited, nope, B has not been visited, mark cur as visited with distance D. So B gets marked as, yep, you're visited, and its distance is 1. Then for all outgoing edges of cur, so B has 2 outgoing edges, D and E. I'm just going to arbitrarily choose to add them to my Q in alphabetical order. However you choose to implement it, it doesn't really matter, just be consistent. So I will add neighbors to the Q in alphabetical order. So first, I'm going to look at D. So if W, so D, has not been visited, nope, it hasn't been visited, add D plus 1, and then the neighbor to the Q. So I add 1 plus 1, which is 2, D to the Q. And I add, so now E has also not been visited, so I add 1 plus 1, so D is still 1, So again, 1 plus 1 is 2. Now it's node E to the Q. And I'm done visiting B. While the queue is not empty, it's not empty, I pop off 2D from my queue. So cur is D with distance 2. If cur has not been visited, nope, D has not been visited, mark it as visited, and it has distance D. So D is 2, little d. Okay, for all edges cur W, so for all outgoing edges from cur, so D only has one outgoing edge, which is C. If the outgoing edge, if the neighbor has not been visited, add D plus 1 W to the cube. So the neighbor has not been visited, so I add 2 plus 1, so 3, and the neighbor to the cube. Okay, and now that was the only neighbor of D, so D is done. While the queue is not empty, it's not empty. I have 2 comma E next, so I pop that off, distance 2, node E. So if cur has not been visited, nope, it has not been visited, I mark it as visited, and it has distance D, which is 2. Okay. For all edges going out of my current node, well, E has no outgoing edges. There's no outgoing edges from E, so there's nothing here. E is done. Okay. While the queue is not empty, it's not empty. I have one more item in my queue. I pop it off, so D cur is 3C. If cur has not been visited, nope, C has not been visited, then I mark it as visited with distance D, which is 3. Okay. For all outgoing edges from my current node, oh, my current node has one outgoing edge, C to E. If that outgoing edge, the destination, has not been visited, nope, I cannot say that. E has been visited. So this is false. E has been visited. I don't re-add it to the queue. And now that traversal is done. While the queue is not empty, oh, the queue is empty. There's nothing else in my queue. Therefore, I'm done. And if I look at my graph, I see I visited every node, and I have their distance away from the starting node, specifically their minimum distance from the starting node. Technically, there are 2 paths that take us to E. We can either go A, B, E, or we can go A, B, D, C, E. So we only keep track of the shortest path in this simple algorithm.